So let's talk about angular momentum. I covered this in my Unit 7C, the momentum aspect of rotational motion. As with a lot of rotational motion in AP Physics 1, we really don't go very deep into angular momentum. It's more of a qualitative treatment. In my C mechanics class, oh my goodness, we spend a lot of time talking about angular momentum. Probably one of the free responses could be an angular momentum problem. It's just a neat topic area, but this is very much a high level review of it. So let's talk about angular momentum. If a body is rotating, if it's moving rotationally, we have angular momentum. Remember, our symbol for angular momentum is capital L. Why? I don't know. If we think about linear momentum is mass times velocity, angular momentum is rotational mass, I, my rotational inertia, times velocity, omega. Again, not a whole lot of calculations where we do angular momentum, not a whole lot of calculations where we actually calculate the momentum of an object. It's always conservation of momentum or impulse. And we have the same thing here. In order to have a change in linear momentum, we have to apply a force for some time period. In order to have a change in angular momentum, we have to apply a torque for some time period. So one thing they need to recognize is if angular momentum is changing, if we have an unbalanced torque being applied. While the torque is being applied, angular momentum will change. And so while torque is not zero, angular momentum changes. This is kind of important to recognize when we get into conservation of angular momentum. Angular momentum is conserved if there's no external torques. Okay, that makes sense. Keep in mind that torque is RF sine theta. Angular momentum is conserved if there's no external torque. Sometimes that's kind of challenging for the kids to recognize. So then I break it down into this. Remember, here's an expression for torque. Is there an external force acting on our object or acting on the system? If there is no external force, there is no external torque. And so a lot of times I don't talk about external torques, although technically that's correct. I still refer to it as, is there an external force that's affecting our system? So let's jump into conservation of angular momentum, keeping in mind we have to have a closed system. Just talked about that. A closed system means my external torque is zero. I like to think of it as my external forces. I don't have any. It's a nice, simple way to think about it. So let's just talk about a couple of examples with conservation of angular momentum. These are a little bit different. With linear momentum, and we're talking about conservation of linear momentum, we're usually dealing with several objects interacting. We either begin with two objects or we begin with one and end with two. There are two masses, two bodies involved in linear momentum. With angular momentum, though, it's a little bit different. A helicopter. It's in the air, a closed system. The propeller is spinning to provide its lift. Now, if the propeller is spinning, that's because there's a force being applied to it from the motor. Newton's third law says there's also going to be a force from the propeller back to the motor in the opposite direction. So in reality, when the propeller is spinning one way, the helicopter should be spinning the other way. This is why if you've ever taken an electric drill and you pulled the trigger real quick, you get a little kickback on it. because of conservation of angular momentum. Now, the reason the helicopter doesn't spin is because of this propeller. This propeller provides a force to counter the helicopter spinning. Some helicopters have two blades. They spin in opposite direction to account for angular momentum, so that the angular momentum stays constant. Otherwise, it would be just a crazy trip. So there's a lot of this conservation of angular momentum. There's a lot of different examples that we can pull out with it. One of the most common are ice skaters when they're spinning. So let's take a look at a short video with this. Okay, keep in mind, conservation of angular momentum means I have no change in angular momentum, which means my initial is equal to my final. Initial angular momentum is initial moment of inertia times initial angular speed. Final moment of inertia, final angular velocity. With the ice skater, her velocity, her angular speed changes because she changes her moment of inertia. She changes her rotational fatness. For the ice skater spinning, her angular velocities change because she's changing her rotational inertia. Here her arms are out. Here her arms are in. And because this moment of inertia is less than the initial moment of inertia, her final speed must be greater than her initial speed, which is why she speeds up. So a real good question is, if you look at the situation of this ice skater spinning, they have more kinetic energy. Their final kinetic energy is going to be greater than their initial kinetic energy. This is not necessarily a clear calculation to do. This is something that you might have to be told, but it occurs. If you look at their final kinetic energy once they pull their arms in, compared to their initial kinetic energy, they have more here. And so the question is, where did it come from? Well, it came from the work they did in pulling the arms in. And that's always a good scenario to talk through. Let's look a little more into comparing linear momentum with angular momentum. This is a very common confusing area. And so I'm going to apologize, although he probably won't be able to hear me. I'm going to apologize to Rudyard Kipling. And I'm going to say linear momentum is linear momentum, and angular momentum is angular momentum, and never the twain shall meet. I apologize, Mr. Kipling. The point is, if we have linear momentum, we have linear momentum. If we have angular momentum, we have angular momentum. Linear momentum does not go into angular momentum. Angular momentum does not go into linear momentum. If we have angular momentum, it's conserved. If we have linear momentum, it's conserved. They don't cross over. Look at the units. They don't have the same units. So there cannot be, it's not conservation of angular and linear momentum. It's one or the other. Now, this is real easy to say. Real easy to say. And the kids go, yeah, that makes sense. Yeah, linear is linear, that's fine. But sometimes it can be tricky to see, and sometimes when you're given a situation, it's a little bit tricky to work with. The nice thing is there's not going to be given problems where we have linear and angular momentum. However, I think it is fair that they will be given some scenarios where they have to interpret what will go on. So let's take a look at that. So we're going to take a look at the idea with linear and angular momentum, what we can expect to see. Let's have a stick. It's on ice. A puck hits the stick right in the middle of the stick. It sticks to it. So in all the cases, I'm going to look at the puck is going to hit the stick and it's going to stick to it. Here's another case. It's a situation where you can change the scenario a little bit to have them analyze what's going on. If it hits the stick and sticks to it and it hits right in the middle, the puck and stick are going to be moving off linearly. We have linear momentum to begin with, the linear momentum of the puck and the linear momentum of the stick. We have final momentum to end with, the momentum of the puck plus the mass of the stick moving off. Linear and linear. That's it. Let's say our stick, though, we still hit the stick right in the middle. It still sticks right in the middle, except the stick is fixed on one end. So in that case, what's going to happen is we're going to have a rotation. And so here's what I'm looking at. I'm looking at the before and I'm looking at the after. I have angular momentum. I'm ending with angular momentum. If I ended with angular momentum, I have to begin with angular momentum. This is a little bit of a confusing thing because the puck is moving in a straight line and the stick is just sitting there. And here's what to recognize. Puck, compared to the turning point, puck has angular momentum with respect to our turning point. The calculation involved with this, we don't do. But this is what they have to be able to recognize. If we ended with angular momentum, we had to begin with angular momentum. So if we begin with linear, we have to end with linear. We have no linear momentum to begin with. None. So we began with no linear momentum. And this is one of the things where it's hard to actually see. People want to say, oh, this linear momentum gets converted to angular. No, it doesn't. The angular momentum came from somewhere. It came from here. Recognize the fact that in this problem, in this system, the puck has angular momentum with respect to my turning point. We're not going to really worry about the math. That's kind of a weird idea to talk about. Last scenario, the puck hits the stick off center, sticks to it. Now, it would seem to make sense that if the puck hits the stick's going to start rotating. So I think it's fair to say puck, stick, rotate. Since it's not fixed, it's also going to move. We're also going to have some linear motion. So here's a case where we clearly end, if we are rotating, we clearly end with angular momentum. If we have linear motion, we clearly have linear momentum, which means we have to begin with some angular momentum and we have to begin with some linear momentum. This problem is can be quite complicated to solve. They're not going to get into doing the math, the solving of the problem, but what they have to be able to say and recognize is, if we have rotational motion, we have angular momentum, it came from somewhere. If we have linear motion, we have linear momentum, it came from somewhere. And so, but the two don't cross paths. And so that's an important aspect with angular momentum, and that's actually one of the harder things to understand. So that concludes my version, what I cover in Unit 7C, rotational motion, angular momentum. I hope this was some help. Good luck.